Now, one more problem from engineering mechanics, problem set 2.6, solution to 2.83. In 2.6, problem set 2.6, we have been dealing with problems by applying moment of a force, that is the turning effect of a force about a given point. And we are not applying the projection method, which we did so in problem set 2.5. So the statement of the problem runs like this. A beam AB, if you can look at the diagram, AB is a beam. It is hinged at A and supported at B by a vertical bar. BC is a vertical bar, not a string. The line is drawn thin, so you might consider this to be a string, but this is not a string, this is a vertical bar. To be kept in mind, is subjected to the action of a force P. Here, at a distance L by 2, the applied force P is applied in this direction, making angle 45 degree with the vertical. Assuming ideal hinges at A, B, C. A, B, and C, these are ideal hinges. Find the force S produced in the bar. What axial force, the tensile force, will be developed in the bar, that is to be found out. Neglect the weight of the beam. The beam AB is weightless. So let me proceed. BC is a, as I just explained, BC is a bar, not a string. So I have written here. Of course, a beam AB cannot be supported in this situation. If this is a string, the string cannot support a beam like this. So ABC is a bar. So that is what I have explained here. Now, why did I say so? You might confuse, you might run into little confusion because this line, the line drawn BC is very thin. It appears as a string, but it is not. It is a bar. Since the line BC is shown as a thin line, one may consider it as a string, but it is not. It is a bar. So, there are three forces. Now, what are the forces? The reaction at A, the applied load P, and the compressive force developed in the bar, and the compressive force developed in the bar BC. So, there are three forces. RA, reaction at A, the applied force P, and the S, the compressive force in bar BC, which is a bar. Now let us produce the line of action of two forces and see where they meet, and therefore the third force will also pass through the same point. Let the line of action of P and S. This is the line of action of a P, and the line of action of the compressive force developed in the bar BC. When produced, they meet at a point E. So, let the line of action of P and S meet at point E, that I have shown here. This is the P, that the line of action is shown dotted here. This is the compressive force, and it will be towards the point B, if you consider point B. And if you consider point E, the same S will be towards E. So they are meeting at point E. P and S, they are meeting at point E. So the conclusion is, for equilibrium, and since the beam AB is in equilibrium, therefore the reaction force at A and the line of action of RA must also pass through the same point E. That is what I have shown here. Now let us take the moment about point A. Means the turning effect of all the forces, three forces about point A. And let us see which force will have a turning effect about A and which will not have. Since RA is passing through point A, moment of RA about A is 0 because it is passing through A. It doesn't have a perpendicular distance from A. This RA is passing through the point A, so it doesn't have a perpendicular distance. So the contribution of RA towards the turning effect about point A is 0. Now, moment of now this P you can split into two rectangular components, one like this P sine 45, one like this as P cos 45. And P sine 40, instead of considering P, you can consider the two components, that is P sine 45 and P cos 45. And if you look at P sine 45 is also passing through the point A. Means P sine 45 also does not have a perpendicular distance from the point A. So P sine 45, which is a component of a P, also does not have a turning effect about point A. But P cos 45, which is to this side, is at this perpendicular distance from A to D. So this will have a turning effect. So moment of P cos 45 about A is 0. I'm sorry, slightly mistaken. This should be P sine 45. Moment of P sine 45 about A is 0 because the line of action of P sine 45 from the point A, P sine 45 does not have a perpendicular distance. Only this will have a turning effect about A. And how much will be that? P cos 45 and times this length AD, which is equal to L divided by 2, L by 2. And what about S? The turning effect of S? This is the line of action of S. And from the point A, the line of action of S is at this perpendicular distance from A to B, that is equal to L. So due to S, this beam AB about point A is trying to rotate like this, anti-clockwise. And how much will be that? S times this perpendicular length, L. And P cos 45, about the effect of P cos 45 about point A will be clockwise like this. And how much will be that? P cos 45 times the length from A to D, that is L by 2. Means anti-clockwise torque and the clockwise torque must be equal because since it is in equilibrium. So that is what I have shown here. Now given AB is equal to L, therefore AD is equal to DB is equal to half of L. Now perpendicular distance of P cos 45 from A is equal to L by 2. Perpendicular distance of S from the moment center A is equal to L. One produces clockwise torque, the other produces anti-clockwise moment. So one produces clockwise moment, the other produces anti-clockwise moment. And since if both are equal, then it will be in equilibrium. That is, sum of the moments about point A is equal to 0. So S times L is P cos 45 into L over 2. Bring L cancels. So S is equal to P cos 45 over 2. Cos 45 1 by root 2. This becomes P by 2 times root 2. So this can be rewritten as 1 by root 2 times P. This can be rewritten as 1 by 2 root 2 times P. And this you put it in a calculator, this comes out to be 0.3535. So your axial force developed in this supporting vertical bar BC, that is a compressive force developed in the bar BC, which is holding this beam AB in equilibrium under the action of the force P is equal to 0.3535 times the applied load P.